Welcome to Module 9. In today's module, we will be studying the chemical equilibrium. Module 9 will be discussed in 4 videos. In the first video, we will introduce reversible reactions and rates of reactions. Then we will introduce the concept of chemical equilibrium. The second video will investigate the different factors in Le Chatelier's principle. The third video will cover the 3 important chemical equilibrium constants. And finally, in the last video, we will discuss the acidic and basic properties of salts and buffer solutions. The learning outcomes for the first part of Module 9 are: identify the concept of reversible reactions, and identify the rate of forward and reverse reactions. Everything around us is related to equilibrium. So before we start the lecture, let's look at this simple example to explain the concept of equilibrium. We have a tank full of gas. Let's call it tank A. It has a pipe and a tap that connects it to tank B, which is empty. When we open the tap, the gas particles start to flow from tank A to B. At the beginning, the gas flows very fast into the empty tank. Then it starts to move slower as tank B is filling up. Eventually, the gas flow appears to have stopped when the amount of gas is equal in both tanks. However, the important question to ask yourself is, have the gas particles actually stopped moving between the tanks? The answer is no. The gas particles remain in constant movement in both directions to keep the amount in tank A equal to the amount in tank B. This point is called the physical equilibrium. So the gas flows from A to B and then from B to A and so on. For chemical reactions, we can use the same analogy. We can say that the forward rate equals the reverse rate and the net change is 0, but the gas is still flowing. The concept of equilibrium is related to reversible reactions only. These reactions form the majority of the chemical reactions that we do. In a reversible reaction, there are 2 directions: the forward reaction, where the reactants are converted into products, and the reverse reaction, where the products are converted back into the reactants. For instance, A reacts with B to produce C and D as products, and this is the forward reaction. As more of the products are produced, they can react together and produce the reactant again in the reverse reaction. So C joins D to form A and B. Initially, the forward reaction is faster than the reverse reaction because there are more reactants than products, but as time goes on, the forward reaction gets slower and the reverse reaction gets faster until the point where they both happen at the same rate. This point is called the chemical equilibrium because the reaction appears to be stopped, but in reality, the rate of forward reaction is equal to the rate of reverse reaction, so no more additional compounds are being produced. We can also call this point the dynamic equilibrium. It is important to note that the concentrations are not necessarily equal between the reactants and the products at the equilibrium point. However, the rate of reactions is equal. Let's look at measuring the vapor pressure at different temperatures. The equation is liquid plus heat forms vapor. When liquid water is heated up, it will convert into steam. This is the forward reaction. If we reduce the heat, the vapor will change back into water in the reverse reaction. At equilibrium, the speed of evaporating water into steam equals the speed of condensing the steam back into water. So we can say that the vapor pressure of the liquid is no longer changing with time. Remember that at the equilibrium point, the concentration of water is not necessarily equal to the concentration of the steam. Let's look at another example of a reversible reaction. Nitrogen dioxide is a brown gas that can undergo a reaction with itself to produce a colorless gas called dinitrogen tetraoxide. The forward reaction produces heat. Therefore, The reverse reaction will require heat. So if you provide heat to the reaction by putting the test tube in a 90 degrees Celsius water bath, the reverse reaction occurs more and nitrogen dioxide is produced and the test tube turns a dark brown color. If you remove the heat from the reaction by putting the test tube in cold water, then the equilibrium will shift towards the forward reaction and produce dinitrogen tetroxide, and the test tube will turn a light brown color. From this example, we discussed the importance of heat in shifting the equilibrium in one direction more than the other. So now let's investigate in more detail what factors affect the rate and mechanisms of reactions. There are 4 factors that affect the rate of reaction: the concentration of the reactants, the temperature, the presence of a catalyst which will increase the rate of chemical reactions, finally, the nature of the reactants, whether they are solid, liquid, or gases. Also, some chemical reactions are faster than others. For example, hydrogen binds to oxygen in an explosive reaction to produce water. On the other hand, iron reacts with oxygen very slowly, leading to rust. We will discuss these factors in more detail later in part 2. For now, we can summarize them in 2 main factors. The first factor is frequency of collisions between the reactants. For chemical reactions to occur, the particles of the reactants need to collide together. So if there are more particles of the reactants, that is, they're in higher concentrations, then there is more chance they will collide together and form the products. In low concentrations, there are less particles, and there will be less frequent collisions. The second factor is energy. Not every collision will lead to a chemical reaction. Sometimes the particles collide but bounce off each other, and no chemical reaction occurs. So for the collision to lead to a chemical reaction, the particles need to have enough energy. We can increase the energy of the particles by raising the temperature or by using catalysts. This diagram shows the relationship between the rate of chemical reaction and time. At the very beginning of the chemical reaction, the forward reaction will be at its maximum speed. No products are formed yet, so there is no reverse reaction. As time goes on, reactants start to collide and form products. Then, the reverse reaction starts to occur slowly as there are only a small amount of products. Then, the forward reaction starts to slow down as there are less reactants, and the reverse reaction speeds up as there are more products. At one point, the forward and reverse reaction rates become equal. This point is the dynamic equilibrium point, as we mentioned earlier. At this point, the reaction happens in both directions at the same rate, so we don't see any visual change and the concentration does not change anymore. So we can summarize all this by saying, any system at equilibrium represents a dynamic state in which 2 or more opposing processes are taking place simultaneously at the same rate. The chemical equilibrium represents the rate of the forward reaction equal to the rate of the reverse reaction. For example, hydrofluoric acid is a weak acid, hence the reversible arrows. When it dissolves in water, it forms hydronium ions and fluoride ions. At equilibrium, the HF is ionizing at the same rate that it is reforming, so the concentrations of HF, F-, and H3O+ are constant, but not necessarily equal. In fact, the concentration of HF is much higher than the concentration of the fluoride and hydronium ions, and we will explain this in more detail in part 3 of this module. Let's check your understanding now. Equilibrium is reached in a chemical reaction when the correct answer is C. Option A is wrong because reactants cannot be completely consumed. Option B is wrong because the concentrations are not necessarily equal. And option D is wrong because the reactions don't stop. They happen at the same rate, so we don't observe any change. This is the end of Part 1 of Module 9. Please proceed to Part 2, which will discuss Le Chatelier's principle.